Yeah, we want to welcome you back. My name is Richard. The channel is Physical Sciences Silver Bullet. Don't forget to subscribe. We are still continuing with the same circuit. Now, when you look at this circuit, remember from our previous question, which is 1.2, we established that the current going through this part was given, and that it was found out to be 1.54 ampere. That one is known because we are going to need it. Now the question says calculate the voltmeter reading V1. Now our V1 is this one. Now when you are faced with such a question, what do you do? What you do is that you list everything you know about this part where V is connected, everything you know. Let us look at what we know. What do we know? We know the resistor across, and that resistor is our R is 3 ohm. That one is known. What else do we know? From the previous question, those of you who have not watched the previous video, we found out that the current going through this this branch is 1.4. So that current is also known. It's 1.54 ampere. So with this information, and you are looking for V, then you have to borrow Ohm's law. What does Ohm's law say? It says that the potential difference across a conductor or in a circuit is equal to those two, the product of those two. So here we are looking for V, but we know I, which is 1.54, and you know R, which is 3. So from here we get our answer. So that is our answer. So the potential difference or the voltage across this 3 ohm resistor is 4.62. Then comes the next question. Then comes our next question. It says calculate the voltmeter reading V. Now our V we are talking about is this one. That's the V we are talking about. And that V is a very fundamental V. It has a name. Some people call it wrongly. They call it total voltage. But generally, it is terminal voltage. It is a terminal voltage. VT. Now, there are several ways of doing this part. Okay. But let's take the easiest way. What's the easiest way? The easiest way is that terminal voltage is given by I total R total, as from Ohm's law. The only difference is that these ones are all total. Now we are looking for I total. The question is, do we know I total? Yes, we know it. We found it already. Do we know R total? Yes, we have it. So that is what we are going to use Now, our I total was found to be okay, our I total was found to be, so this is our I total or total current, which is 3.34, and our total resistance, we found it already, it was 8.23. So what do? We just substitute in there and we get terminal voltage from this substitution, which is 3.34 times 8.23, giving you, from the calculator here, 27.89 volts. Now, this is what we have as our terminal voltage. Then comes this question. When the switch S1, this switch here, S1 is open, the voltmeter reading changed to 30 volts. Remember previously we calculated it as 27 point something. Now what happened here? Opening of the switch has increased it. Now the question comes, give a reason for the change in the voltmeter reading when the switch S1 is open. Okay, I want to tell you some stuff here. Okay, we need to remember that when the switch is open, this part is still connected. So what do we say? Current is this part is still connected, but there's something we have to know. It is connected to a voltmeter. And what do we know about voltmeter? Voltmeter has infinity resistance. It does not allow current to go through it because of that very high resistance. So in other words, it is connected, but no current passes. Now, when there's no current passing, it means there's even no current passing through this internal resistor. And the internal resistor is the one responsible for the drop in the voltage through the Ohm's law principle. The voltage is equal to IR. So in other words, when there's no current passing through this battery, through this internal resistor, it means that this internal resistor is not dropping any current. There's no voltage responsible for the voltage drop caused by this internal resistor. So how do you answer this one? Then we can say, because the question says, give a reason for the change in voltmeter reading when the switch S1 is open. So I say with the switch S1 open, there is no current passing through the battery. Battery stock internal resistance, which would cause voltage loss or potential difference drop. So now now we know why there is a difference in the reading the moment you open or close the switch. The cause is internal resistance. When it is in play, in other words, when there is current going through it, there is voltage drop, because any resistor through which current is passing, there is a voltage responsible for that. So that drop is caused by this internal resistor. So the moment there's no current passing through, there's no voltage drop. So we go to the next question. Then comes this question. It says, calculate the internal resistance of the battery. So for this case, we borrow the general equation, which says that EMF is equal to this one, which sometimes we call VT, or terminal voltage, which is current times total current times total external resistance plus total current times internal resistance. So we can make, we are supposed to make use of this. So when you have to remember something which is very important, that with the opening of this switch and the voltage increased, that the voltage registered when there is no current going through the battery, that voltage is what we call EMF, electromotive force. I repeat, once you open the switch S1 and you stop the current to go through the battery, the voltage you register under that circumstance is the EMF. So in this case, what do we say? We know the EMF of the battery, and it is 30 volts. And from the previous calculation, we found the total current, which was 3.34. So our total current, we did it already. It is 3.34 from our previous calculations. We also found something. We found the total resistance, if you can recall. And what did we find? We found it as 8.23. 8.23 ohm. So these are all we need to calculate our internal resistance, this one. So from what we can assess, we know we have this. You have everything here apart from the internal resistance. So when you substitute, you're going to get 30. Our total current is 3.34 times our total resistance, which is 8.23, plus our total current, which is 3.34 times internal resistance. So from here, you perform the computation to get the internal resistance. So this is what we get after computation, and our internal resistance has been found to be 0.75 ohms. So another question is coming, but because we don't want to make these videos very long, we would advise you to go and view our next video. So this one is going to be cut here. Don't forget to subscribe.